Otherwise, I'm going to have to take lots of breaks so you can all scurry up to the front and ask those really interesting questions. So I'm going to try and finish this section. It's unlikely that I'm going to do it now before dinner, unless you want a late dinner. No, I didn't think so. Because really what I want to do tomorrow is start on the Hamiltonian-based methods and then move on to the differential geometric methods, which is the really cool stuff. But let me finish off with the sort of vanilla MCMC. So just to recap, I gave you the background, and we built up right from scratch the Metropolis-Hastings algorithm, right? From knowing that a sufficient condition for an invariant distribution of a Markov chain to exist, then reversibility is all that's required. And so we developed a skeleton of a transition operator, and we built it up by defining a particular function based on a proposal mechanism, and then to enforce reversibility, this additional probability, this acceptance probability, which then gave us the well-known Hastings ratio, and we came up with the overall transition kernel, which would give us the invariant distribution that we were interested in. And we then looked at some variants of that. We looked at products of kernels and how a product of kernels will still retain the invariance of the joint distribution of interest. And we looked at mixtures of kernels, which again gave us a means of being able to start to address problems like this here, which are far more prevalent in all areas of application than we would imagine. So let me now move on to another technique which is employed, and it's called data augmentation. Now, for those of you who know about the EM algorithm, you know about data augmentation. Okay, so the EM algorithm is basically a means of maximum likelihood estimation where there is missing data. And so we augment the model with expected values of the missing data. And so we use this trick in MCMC as well, to good effect. So let's consider a target density, right, pi of theta. And for some reason, unbeknown to us, we would like to have a Gibbs sampling scheme because we're too lazy to really try and engineer an efficient proposal mechanism. But it turns out that the conditionals, or the exact conditionals, are non-analytic, and we cannot simulate from them from pi of theta. But it turns out that in some cases, if we augment our model with another random variable, call it phi, and the augmented target density, pi of theta and phi, so let me just stress that the parameters of interest in our statistical model are theta, and these phi's are auxiliary, right? They're ancillary. They carry no information at all about the model. They're not related to the underlying model. But what it does is it provides a joint distribution on the parameters of interest and these auxiliary parameters that enables us to devise a Gibbs sampling scheme where the exact conditionals for theta given phi and phi given theta emerge in a natural way. And because of that, and because of the fact that the desired density that we're interested in, pi of theta, can be obtained by just marginalizing the joint density with respect to the auxiliary variable. So, if we develop a Markov chain whose invariant distribution is this one here, and we draw samples theta n and phi n from that invariant distribution, if we throw away all the phi n's, and we might as well because they're auxiliary to the model, they're of no use to us, at this stage, then what's the distribution for each of the phi ends? Well, the theta ends. Well, it turns out that the distribution for each theta n is just going to be the integral of pi of theta n and all values of phi, and we integrate with respect to that, it just turns out to be pi of theta n. So this is a very nice result. We simulate from this augmented distribution, we ditch the auxiliary variables, and what's left, the variables of interest, are distributed according to the target density of real interest. So this is a nice result, and it's one that's used actually fairly regularly in statistical practice and in machine learning practice as well. I should also just point out that I kind of have a bit of a Jekyll and Hyde character here, in that I straddle both the computational statistics and the machine learning camps, and I see them pretty much as the same in many ways, unlike Neil. So sometimes when I talk about statistical problems, I'm really referring to machine learning problems or whatever, okay? That doesn't make me a bad person. Okay. So the main point of this, and the main point with the EM algorithm, is that we need to find a representation of what's called a completion of the model, a completion of the parameter space, that allows us to obtain the exact conditionals, pi of phi given theta and pi of theta given phi, and that these can be sampled from in a nice natural way. So I'm going to look at a model that's fairly well known in the machine learning literature. In fact, it's fairly well known in the literature in general, and that's probit regression. How many of you know about probit regression? Okay, so maybe not as many as I thought. The grown-ups do, that's for sure. Or the old guys do, I should say. But okay, well, probit regression is it's a means of modelling binary response data, and it is used as a means of classifying data in a parametric way. So we would say that we have some binary response variable, so that's our class label, if you will, t, which would take on values 1 or 0, and we have a set of features, covariates if you want to kid on, you're a statistician, we call them x, and then a set of parameters associated with those features, beta. And the probability that the response variable, the probability that the class label is going to equal 1, given the current features and the current parameter values, is equal to this probit function here. Now this is just the cumulative distribution function of a normal density where we're integrating from minus infinity up to the value x beta. And that's bounded between 0 and 1. Okay? And this is just, I mean, we could replace this with a more natural function, which would be the logistic function, right? But we'll stick with probit regression for the time being. And what we want to do is, given a whole series of samples of our features x and the corresponding class labels associated with each of those, we want to get the posterior distribution of beta given all of the x's and all of the t's, right? And we can't do that analytically. And we don't want to resort to any variational approximations or Laplace approximations or anything like that for the time being, despite all those skeletons in my cupboard or wardrobe rattling away. So we want to be able to sample and get the full posterior over these betas. Well, we could just set up a Metropolis-Hastings algorithm. It would be very straightforward. Wouldn't take much. But we can do something a little bit more clever, in that we could devise a Gibbs sampler for this probit regression by employing this data augmentation. And the way we do it, the way we complete the data is as follows. We introduce the auxiliary variable, we'll call it y, and we'll say that y augments the model such that beta transpose x plus some random element, some error term, is going to equal this auxiliary variable. And the error term is just going to be a standardized normal variate. Okay? Furthermore, we'll say that the class label, right, for the ith example, so ti, is going to equal 1 if the value of the auxiliary variable for that example is greater than 0. And we'll say that the class label equals 0 if the auxiliary variable is smaller than or equal to 0. So that means then that the augmented density, P of t, right, our class labels, and the auxiliary variable, given our features, so these are set, right, these are fixed, and the parameters of the model, beta, right, this joint distribution can be decomposed in this form here. So we can say that the joint distribution is going to be the probability of our class label given the auxiliary variable, right, multiplied by the probability of the auxiliary variable given the features and the current parameters. Now, by the way that we've defined the augmented model, the probability of the class label given the auxiliary variable is just going to be a delta function. Right? So it's going to be a delta function if t is 1 when y is greater than 0, and it's going to be a delta function, it's going to be 1 when t is 0 and y is smaller than or equal to 0. Okay? So we have a delta function for this probability here. Now what's the probability for the auxiliary variable? For those of you that were awake and were paying attention to Neil's talk, you should be able to tell me in the blink of an eye what this distribution is. What was that? Top of the class. You can buy me a beer later tonight. So, indeed, so this distribution is just a normal distribution over y with a mean of beta transpose xi, and because this is a standardized normal variate, the variance is 1. Brilliant. So the joint density over n examples of features and class labels is just going to be the product of the overall joint density, which I've written like this. Now, I made a deliberate mistake in the text there, because I knew I was coming to a summer school full of absolutely brilliant young minds, and I thought I'll put in a very, very simple schoolboy error in that equation and see how long it takes them to find it. Well, that's encouraging. You didn't find it. So it's here, is that these exponents should be ti and 1 minus ti. Okay? So what we're saying here is that if ti equals 1, then this is just going to be 1, and this is just going to equal the delta function times this normal distribution. And if ti is 0, then this is just 1, and we're just left with this delta function and this here. And we just ripple through all the examples. So that's our expanded likelihood. Now, of course, we would be putting a prior on beta, but I'm just going to ignore that for the time being. So at the moment, I'm just going to assume that the prior is completely flat. We wouldn't normally do that as good Bayesians, but just to keep things nice and simple and get the basic concepts, we're just going to now derive the full conditional. So this is not the target distribution that we want, because the auxiliary variable's here. So we need to derive the full conditional for beta, given our target variables, the auxiliary variable, and then all of our covariates. Now it turns out, if we just look at everything that's here, so beta just occurs in this expression here, and of course the t's are here. So in essence, the conditional is just going to be the product of all of the normal distributions. Now what about, and yeah, that's proportional to that, and of course, if you were paying attention to Neil's talk, you would recognise this immediately as just the posterior for a multivariate Gaussian that has a likelihood in this form here. And this, of course, is just the least squares solution. And this, of course, is just the covariance of the least squares solution. You see here that the target is no longer the binary variable. The target is now the auxiliary variable. So we need to be able to sample the auxiliary variable. And what's that? What's the conditional for the auxiliary variable? Why? Well, if we just, again, look at the terms where y occurs, we've got this delta function, and we've got this normal distribution. So it's going to be a delta function times the normal distribution. And a little bit of manipulation shows us that for the values of t which are equal to 1, then each of the y's conditioned on beta, t and x is just going to be equal to a truncated univariate Gaussian with a mean of beta transpose xi and a variance of 1. And when t is 0, then it's just a truncation in the opposite direction. So the overall Gibbs sampler turns out to be something really easy. We sample beta from this multivariate Gaussian, whose mean is the least squares solution, right, for the current value of the auxiliary variables. The covariance structure never changes. And then, given beta, right, given the value of beta that we sampled, we sample the auxiliary variables from these truncated normals depending on the value of the class label, whether it's 1 or 0. Okay? And, well, that's cool, because all we need to do, this is easy to sample from, and this is relatively easy to sample from as well. We don't have the hassle of thinking about, you know, if this is a fairly large number of features, so if I was a statistician, I would say a large number of features is 10. Or if I was Neil, I'd say 3,600, yeah, absolutely. So devising a metropolis sampler for that 3,640 dimensional random vector is going to be non-trivial. We'd be spending a lot of time devising product kernels and then tuning each of those. This looks like a blessed relief, because all we need to do is just sample from our multivariate Gaussian, our 3,640 dimensional multivariate Gaussian, and then just sample from these one-dimensional Gaussians as many times as we have samples, and we're done. So that looks great. And typically it is pretty great. However, can anyone see the fly in the ointment here? Think of the correlation structure. Well, this sampler, although it can be written in about 4 or 5 lines of MATLAB and can run very nicely, it's doomed from the start. And it's doomed from the start because the auxiliary variable is directly correlated with the parameters of interest. So we have an immediate correlation structure in our exact conditionals. And so what you get is a chain that mixes really, really, really slowly. So despite it being very elegant and looking really nice and 4 or 5 lines of MATLAB code and it's off and running, the mixing and the Monte Carlo error that you would obtain is really pretty grim. So there's been a whole load of work on trying to get around that problem by doing various things. But what I'm going to focus on, and in the last 10 minutes, I'm only going to be able to look at one of them, So tomorrow we'll start on the Hamiltonian scheme. But for now, I'm going to think about the whole idea of an adaptive proposal distribution. And someone actually asked that question in the break session, and it was a great question. Now, one of the problems with adapting a proposal distribution is the following. So we're running our sampler, and we're finding that the sampler isn't moving very well. It's very sticky. So we'll use output from the chain to maybe estimate, I don't know, the mixing coefficient in our mixture of kernels, or we'll estimate the scale for our proposal distribution. What cardinal sin have we committed? You were laughing. What's the answer? She's not laughing now. Well, of course, the problem is that we've got a Markov process, we've got a Markov chain, and we are now defining the proposal distribution of the transition kernel based on a history which is longer than just one step. So we're destroying the Markov property straight away. So what we would like then is to have an adaptive proposal mechanism that retains the Markov property and so forth. And one of the really beautiful ways of having an adaptive proposal mechanism is to exploit a discrete form of a diffusion process. And in particular, a Langevin diffusion process, which is defined by this stochastic differential equation here. Okay? So this is a very classical stochastic differential equation that tells us that an increment of d theta at some time t is equal to this drift function. And this drift function is the gradient of the log of my distribution of interest, so my posterior distribution, we'll say, right? Computed at the values of the process at theta t, and then we have the time element, so that's our drift. And then we have this Brownian motion, so this independent Brownian motion which is driving the process. And what's beautiful about this here is that if we, so let me just say that the solution, right, so the solution paths of this diffusion process are such that they are distributed according to pi of theta. Now, again, for the sort of problems that we would be working on, where pi of theta, has structure, is quite complex, then there's no way that we can solve this. So what we can do is we can employ a discrete form of integration, right, to numerically integrate this diffusion. So the standard kind of first order case would be to use an Euler-Maruyama integration. So we just have a step size epsilon, and we build up the overall path of the diffusion in this manner here. So at a particular time tau, right, we have the values of our random variables, which is our parameters. We have the value of our drift function, which of course is the gradient of our posterior. And then we have this innovation process, which is now, because this is independent Brownian motion, this is just isotropic, standardized, normal variates. Now, the problem here is that unless epsilon, well, as epsilon tends to 0, then we will recover the solution paths of the continuous SDE, and therefore, the target distribution will be the solution for this. But in all practical aspects, epsilon, the step size, has got to be kind of finite, and because it's finite, then the distribution of the paths that we simulate or we integrate from this are going to be biased. So they are not going to be pi of theta. But we can correct that bias in a way that you met only about an hour ago. But what I'm going to do is I'm going to say, well, I'm going to use this as a proposal mechanism, right? Because this is just a random variable with a mean of theta at tau plus this component of the directional derivative. And then it has a covariance structure which is just going to be isotropic scaled by epsilon. So my proposal, based on this discrete form of this Langevin diffusion, is just a normal with a mean, as I described here, and this isotropic diffusion. And I can correct the bias just by using the acceptance probability. So I'm using the same trick that Hastings used when he devised the Metropolis-Hastings algorithm. To enforce reversibility, we use an acceptance probability to ensure detailed balance, and we do the exact same here. But what's really cool about the proposal mechanism here is that it's adaptive, right? The direction, so if you think about the Metropolis-Hastings algorithm, it's a random walk. It's completely random. It's indirectly driven by the density of the target distribution, but the proposal mechanism is completely random. Here, on the other hand, our proposal mechanism, the mean, is driven by the gradient of our target distribution. So that means it's going to be far more efficient, right, because it's going to be following the directional derivative into regions of high density. And that directional derivative is going to change at each point in the Markov chain, right? So it's adapting locally. And this is really cool. And you'll see there's lots of empirical evidence to show that this works far better than a random walk. However, there's still a little problem with it. And can you see what that is? Look at the innovation process. It's the same variance in all dimensions. And if we've got a distribution like this here, then we end up with the same problem that we had with the random walk. So although now we're taking directional gradient information into account, we are still going to be driven by this spherical cloud, right, which is based on the square of the integration step size. So we still have to get around this problem here. We've got around this problem, kind of, but now we still have this problem here. And one way that mathematicians get around this problem, it's a problem that's faced in the solution of partial differential equations, where you can have ill conditioning. And so what they use is a matrix transformation to precondition the systems of equations. And what is done in the MCMC literature is that they would multiply the directional derivative and the standardized normal variates by a preconditioning matrix M. So multiply by M the directional derivative, and then the square root, so a Cholesky root or what have you, of M here. Now the problem is, how do we set M? This is a matrix now. It's no longer one parameter. It's a matrix. How do we do this in a systematic way, right, without any engineering ad hocery? And being a mechanical engineer, I think I'm quite entitled to talk about engineering ad hocery. And indeed, how would we tune this matrix when we're in the transient phase of the Markov chain, and we could be in the transient phase for quite some time, and then once we enter the stationary phase, when we want to start sampling from the invariant measure, how do we tune that? And it's not at all clear. And a lot of people have really worked on this problem and tried to figure out how do we get around the problem of the scaling of the covariance structure, and how do we get around the problem of the scaling of the covariance structure at each point, at each phase in the Markov process? Well, it's going to have to wait till tomorrow. So I hope it keeps you awake a little bit tonight. So let me just close by saying I've given you probably all the vanilla MCMC that's available. I'm not going to touch sequential Monte Carlo. I'm going to mention that a little in my final lecture. But hopefully you've got a good intuition now for the drivers underneath it. Tomorrow's lecture, I'm going to start off with the Hamiltonian or the hybrid Monte Carlo method, which is the darling MCMC method of all those that publish at NIPS. And then I'll get on to the really cool stuff for the rest of tomorrow's lecture. So it's 7 o'clock I finish, not 7:30. I'll go on to past. I'm quite happy to go until 7:30. Okay. Well, I guess it's dinner time, and I guess you're all tired, so I won't extend the agony any longer by asking if there are any questions. But if there are, grab me tomorrow, or grab me later on this evening. But if you see me scurrying away quickly, I'm in no mood for questions. Okay?